Here we have solved the linear harmonic oscillator in position basis, and in the last class we have also worked out the problem or outlined the problem in momentum basis too. In both the formalism we have solved a differential equation. This is the Soidinger description of quantum mechanics, in which the problem is ultimately converted into differential equation, and we solve the one solves the differential equation subject to the boundary condition and gets the wave function of the system. We have applied such techniques for many one-dimensional problem as well as for a harmonic oscillator problem in position basis as well as in momentum basis. Today we shall discuss another formalism of quantum mechanics known as Heisenberg mechanics or matrix mechanics, or the Heisenberg formalism of quantum mechanics. In this formalism we do not assume any explicit form of the operators, rather we basically assume that the commutator relation between x and p, and based on this we use the commutator algebra to arrive at the same result. Let us start with the Hamiltonian of the harmonic oscillator. Harmonic oscillator Hamiltonian is p operator square upon 2m plus half m omega square x operator square. We write it as 1 upon 2m m square omega square x operator square plus p operator square. Had these two been scalar numbers, then a square plus b square can be written as a plus ib into a minus ib, but this is not possible for operators, because this relation assumes that ab is equal to ba, the commutator between two quantities. But in the case of operator, they may not commute, and in fact x and p do not commute. Keeping this in mind, we calculate this quantity m omega x minus ip times m omega x plus ip. So this is first term. When it is multiplied, it is m square omega square x operator square. Then this term, this is simply p operator square. Then we consider this multiplied by this, it is I m omega, this is xp, and when this is multiplied by this is minus px. So this is m square omega square x operator square plus p operator square plus I m omega. This is xp commutator. Xp commutator, we know that it is equal to IH cross. So this quantity is simply this is minus mh cross omega. So this is equal to how to write the Hamiltonian? When this is divided by 2m is the Hamiltonian. So the Hamiltonian is written as h this is the Hamiltonian, which we write as this plus this. So this is 1 upon 2m Now the unit of Hamiltonian is h cross. Hamiltonian and h cross omega has the same dimension. So if we write the Hamiltonian in dimensionless form, Hamiltonian is h upon h cross omega. This is dimensionless Hamiltonian. This is equal to when we divide it by this is simply plus half. We define two operators like this. Where a plus minus operator is defined as for plus sign it is minus, this is equally divided into two halves. This quantity is one by root 2 taken out, so this is m omega h cross square root times x cap, and this is minus plus I 1 upon m h cross omega p. When we solve Soidinger equation in position basis, note that this part is alpha, and when we solved it in momentum basis, this is beta. So they are indeed position dimensionless position. Where Q is equal to Q operator is defined as m omega h cross x. This is dimensionless position. Position operator, and capital P is equal to 1 upon m h cross omega small p is dimensionless momentum operator. It is interesting to see what is the commutator relation, basic commutator relation in terms of Q and P. I will be coming to this point afterwards. So the quantity A plus minus is defined in this term. It is the dimensionless. It is the dimensionless form of position and momentum operator. So we can write this equation. This equation gives you H, the Hamiltonian, is equal to H cross omega A plus A minus plus half. This can also be written, check it by yourself, A minus A plus minus half. These are the two alternative forms of the Hamiltonian. So this much we have done. This operator A plus is called the raising operator or the creation operator or the step up operator, while A minus is called the lowering operator, annihilation operator or step down operator. The reason will be cleared soon. So we rewrite this Hamiltonian as the harmonic oscillator Hamiltonian is now written as H where A plus minus is equal to 1 upon root 2 Q minus plus IP, and for Q and P we have this definition. So now first we consider what is the commutator relation of Q with P. Q with P, for Q we write m omega h cross times x so we have scalar factor taken out, m omega h cross then x p, actually it is px. If we consider this, m cancels, omega cancels, so 1 by h comes, so it is in the denominator, it is, and from this it is I h cross, so it is I simply. You know that the product, when we multiply x with p, the dimension of xp is action, that's h has the dimension of action. When we have recasted the equation in the dimensionless form, the right hand side is also dimensionless. In matrix mechanics, the commutator algebra plays an important role. First, we want to find out the commutator between A plus and A minus. Before going to that, I would like to recall that A plus minus is equal to 1 upon root 2 Q minus plus IP. If we take the Hermitian conjugate of this, then this is 1 upon root 2 Q dagger. This will be Hermitian conjugate, means plus minus, because I is replaced by minus I, and Q and P are Hermitian, so it will have Q plus minus IP, that is A minus plus. That is to say, the Hermitian conjugate of A plus is A minus, and Hermitian conjugate of A minus is equal to A plus. So these A plus, A minus are not Hermitian operator, but one is the Hermitian conjugate of the other. Keep this in mind. This is an important property, will be utilized up. Now we will look for the commutator of A plus, A minus. We write it in dimensionless form. It is for here we will have a root 2, and so this is half. Then the commutator of Q minus IP, Q plus IP. This commutator is in the form A plus B commutator with C plus D. So the commutator is AC, AD, BC, BD. These are the four commutators. So the writing this In this fashion we get half. In quantum mechanics we will be very careful in using third bracket. Third bracket means the commutator bracket. So this is q commutator q. This is the commutator of this with this and this with this. This is I q commutator p. Be careful about the ordering. And then this with this, it is minus I p commutator q, and finally it is plus p commutator p. So this is 0, this is 0, this part is I, and this part is minus I. So this is I into I minus 1, this is again, this is minus 1. So this is the commutator relation. So we make the summary, keep the summary there. Now we shall consider the commutator of Hamiltonian with A plus minus. Hamiltonian commutator with A plus minus. Now let me consider it plus first. That will be easier for you. I write Hamiltonian in this form. This is for Hamiltonian, this is A dagger. Now this is a scalar, so it commutes with this. So we need not to consider that. So an H cross comes out. So we have commutator of A plus, A minus commuting with A plus. We know from the relation that AB commuting with C, the relation is A BC commutator plus AC commutator B. We have already worked out lots of such commutator relation under the heading of quantum theory, Commutator Algebra 1 and 2. So keeping this in mind, this is H cross omega common. Then the commutator with this with A plus coming from left. And then commutator of A plus with A plus and A minus coming from the right. This is 0 and this is plus 1. As we have obtained the commutator of A plus, A minus is minus 1. So when we all interchange this, the sign will also interchange, and the result is plus H cross omega A plus. Instead of A plus, if we were using A minus, that is commutator of A minus, then it is A minus, it is A minus, it will be A minus, and this will be A minus. In that case, we find that this would be equal to 0 and this would be equal to minus 1, and the result would be minus H cross omega A minus. So we summarize the result as A plus minus equal to, this is the another important commutator relation. So till now we have find out we have expressed of the Hamiltonian operator in terms of two operators a plus minus, and we have assumed the commutator, or we have proved the commutator relations of the operators a plus and a minus amongst themselves and with the Hamiltonian itself. Now we come to another operator. The operator is called the number operator. Later on we will see that this represents the number of photons in the system. The operator n is defined as a plus a minus. We first want to have an idea about what is the what is the eigenvalue of n operator, number operator. Let us call that n operator, when operates on its eigenket, gives you eta times eta. So eta is the eigenvalue and this is the eigenket. So this is the operator. So writing explicitly, we have n eta. So we have n eta means a plus a minus operating on eta. Let us call that a minus operating on eta gives you another ket. It is an operator when operating on a column matrix, gives you another column matrix. So this is another eigenket. If we take the Hermitian conjugate of this, then the relation is this ket will be replaced by bar, and then a minus will be replaced by a minus dagger, and this will be the ket will be converted into bar. That is, these are the row matrices. But a minus dagger is actually a plus. So this is that I have already shown. So if we multiply this equation by eta from the left, we get and on the right hand side we will have this is the norm of a vector and is a positive quantity, and the eigenvalue equation of this leads to that it is eta times or eta is equal to is obtained as the ratio of the norms of two same vector and it is greater than equal to 0. The equal to sign occurs only when it is a null ket. So we conclude that if we define a number, its eigenvalue is non-negative. So it can represent the photon number that I will come to afterwards. So this is all about number operators, and now we come to the Soidinger equation in energy basis. So we define n operator is equal to a plus a minus with n operating on eta This is our conclusion. Now we write the equation as that Hamiltonian operating on a kth state gives you the energy value times the same kth. We write this as the energy eigenkth. Actually, the time-independent Soidinger equation solution of time-independent Soidinger equation is the solution for energy eigenkets. Now we want to see what is the action of A plus minus acting on E. A plus minus is an operator, so when it operates on it, it is a square operator. When expressed in matrix form, it is a square operator because it is the combination of Q's and P's. They are square matrices, so there are some differences. Again, a square matrix. So it is a square matrix. Operating on it, we will find another eigenkth. So we will have an eigenkth. Say it is E prime. Our aim is to how E prime and E are related. But otherwise it will be E plus minus would be better. How E plus minus is related to this? This is our question. The question that we want to ask. So first, the energy eigenkth relation is H. E is equal to E. So this is the energy eigenkth. This is energy eigenvalue, and this is the basically the time independent Soidinger equation. Now, to know how it works, we use this expression, that is H A plus minus operating on kth E gives you so this we consider this commutator relation and operate from the right by the eigenkth E. What happens? First term H A plus minus E minus A plus minus H E is equal to plus minus H cross omega A plus minus energy kth E. This is know that it is E times kT as per this equation. So this relation becomes in this case it is or we write take this on the other side. This is E plus minus in our notation. What does this mean? This means that E plus minus, the kth E plus minus, which is obtained by operating A plus minus on E, is an eigenkth of the Hamiltonian with eigenvalue That is, when A plus operates on a state E, A plus, or this is an state E, when A plus operates on it, it takes the energy level 1. A plus operate When A plus operates on it, it takes to an energy level E plus H cross omega, and when E minus operates on it, A minus operates on it, we go to one step down. So if the energy of the system is E, then by operating the A plus on the state E, we get another state in which one photon is added to the system. That's why A plus is called creation operator, that is, a photon is created within the system. On the other hand, here a photon is removed from the system. So a photon is annihilation operator or lowering operator or destruction operator. So that much we have obtained, that starting from one state, a particular state, if we operate A plus successively, we can go for each time we operate A plus, we will go one step up, another step up, and so on and so forth. That is, you operating A plus 5 times means 5 photon each of energy h nu is added to the system, and operation of A minus 3 successive times means that the 3 photons are removed from the system. But a ground state is one at which the system has minimum amount of energy. So if the system is already in its ground state, then if we operate by A plus on the ground state, let me first keep the summary of it, then I will go to others. The summary is that A plus minus operating on E gives you another state. There will be some constants. Constant is that, I will come into the constant. So now if we consider the ground state of the system to be such that the corresponding eigenkette is written by E0 for ground state. The eigenkette is E0 and the eigenvalue is E0. So the ground state equation is H operating on E0 gives you E0 times this. Now if E0 be the ground state, then the system doesn't have any photon. The system energy, as we know from our earlier work, is only the fluctuation energy. So there is no question of removing any more photon from the system. That is, the ground state has the signature that A minus operating on E0 will give you a zero ket, a null ket. It is a null ket. On the other hand, if we use A plus on E0, we will get the first excited state. Now we write H. This part is for H. We know the definition of H is this. Now A minus operating on is 0, so we will have this half H cross omega E0 is equal to E0 Since this is not a null ket, ground state has a this is not a null ket, we will find that E0 is equal to half h cross omega, the ground state energy. You see that the old things are getting back, we are getting back the old thing in a different fashion. Now if we write a plus operating on E0, then what we will get? We will get E1 ket. In E1 ket, the energy of E1 ket has the eigenfunction this. We are not still saying about anything about E1, that will come to afterwards, but E0, E1 is E0 plus h cross omega. So this is 3 by 2 h cross omega. Similarly, if we write E2 with E2 is equal to E1 plus h cross omega, that is 5 by 2 h cross omega. So we see that the minimum possible energy is half h cross omega, and the subsequent energy levels differs from it by the addition of a whole number of photons. That is the energy level. The ground state has this energy half h cross omega. First excited state has energy 3 by 2 h cross omega. Second one has 5 by 2 h cross omega. So the energy levels are equispaced, and the spacing between the two consecutive levels is h cross omega that we obtained earlier. So we have solved the harmonic oscillator problem so far its energy value is concerned in a different approach. In the next class we shall start for finding out the eigenfunctions and the other related things.